Okay. So for this video, I'm basically doing the rest of the stuff until the quotient group section. So, which is essentially 8-1 and 8-2. So the cosets and normal subgroups in this video. So let's get to it. This is in the last video, but I figured I'd start here. Theorem 728, no permutation in Sn is both even and odd. It's like you can think of it as exclusive or XOR. Permutation in Sn is even, XOR, odd. Oh my gosh. And an alternating group of permutations is the set of all even permutations in Sn, and it's denoted by An. Theorem 729. An is a subgroup of Sn. Duh. The order of An is n factorial divided by 2. So An is a subgroup of Sn of order n factorial divided by 2. Now we're getting into the new stuff. Definition of congruence mod K for a subgroup K of a group G. We can say A is congruent to B mod K if and only if A B inverse is in K. So basically, we say in like proof form, let G be a group and let K be a subgroup of G, and let AB belong to G. So A is congruent to B mod K if and only if AB inverse is in K. Theorem 8.1. Let K be a subgroup of G, where G is a group. The relation of congruence mod K is reflexive, symmetric, and transitive. So A congruent to B mod K is an equivalence relation. So going through those three things, reflexive means A is congruent to A mod K for all A and G. So A is congruent to itself. And symmetric, you can write it forwards and backwards. It means the same thing. A is congruent to B mod K, B is congruent to A mod K. And transitive, it's this is kind of just like the basic logic. If A is congruent to B and B is congruent to C, then A is congruent to C mod K. Ka is called a right coset of K and G. The congruence class of a mod K is the set B, so the set all B's in G, where B is congruent to A mod K. We can say this is the same thing as all B's in G, where BA inverse is in K. We can say this is the same as all B's in G, where BA inverse equals some element in K. We can also say this is all B's in G, where B equals KA for some K and K and A and G. And then we can say that that all B's in G, where B is congruent to A mod K, that's the same thing as all KA, where K is in K. So the congruence class of A mod K is the set KA. That's a right coset. So when the operation is addition, so because this was the like every other group operation but addition notation. So this in the addition form, we say K plus A instead of KA. So we would say then the right coset for an additive group is K plus A, which is the set of all K plus A of where K is in K and A is in G. Theorem 8.2, let K be a subgroup in G, let AC belong to G. Then A is congruent to C mod K if and only if KA equals KC. And you would use reflexivity and transitivity to prove. How do you use this theorem in questions? Yeah, I don't know. Corollary 8.3, let K be a subgroup of a group G, then two right cosets of K are either disjoint or identical. So some remarks on that. If two right cosets have literally one element in common, they must be identical. Because remember from the last video or the last section, disjoint means they have nothing in common. And we would prove this theorem by saying that like we've got like two cases. So if Ka and Kc are disjoint, there's nothing to prove, showing that they're either disjoint or identical because they are disjoint. That's obvious. If they're not disjoint, we want to show that they are identical. So to do that, you suppose they're non-empty and then say that there's some element B in Ka and Kc. And then from there, define B as congruent to A mod K and B as congruent to C mod K. Then use transitivity and symmetry to finish. What did I say? Oh, yeah. So for this theorem's nice because she's going to have on the exam, I'm pretty sure, a question where it's like, are these cosets disjoint, identical, neither, or both? And the answer is never going to be neither or both because it literally has to be one or the other. Theorem 8.4, let K be a subgroup of G. Then we can say two things. We can say G is the union of the right cosets of K, meaning G equals U sub A and G for all of the KAs. And for any element in G, where A is in G, there's a bijective map or function, we can say, of F mapping K to KA. Theorem 8.4, this implication of the second one, like talking about the mapping, that implies that K is fine, that if K is finite, then any two right cosets contain the same number of elements, meaning order of K equals order of Ka equals order of Kb for all A, B, and G. And the additive version of this is K, even like K plus E or K plus 0. Order of K plus 0 equals order of K plus A equals order of K plus B for all A, B, and G. Index, we're defining that now. Let K be a subgroup of G. So that notation, bracket G to K is the index of K and G. But I'm just going to call that index from now on. So this means that, so the index is the index of K and G, meaning the index of G to K is the number of distinct right cosets of K and G. So it's literally almost like, it's literally just straight up the number of the distinct ones. Like how many are there? Almost like order or cardinality. How to find it? You can actually compute all the cosets and count the distinct ones, or you can use Lagrange's theorem, which we'll go over in a sec, which is now. Lagrange's theorem. Let K be a subgroup of G, and let G be a finite group. This only works when G is finite, so very important. If G is not finite, then you've got to do the long way. So K is a subgroup of G, G is finite, then the order of G equals order of K times the index of G and of K. This implies a few things. Order of K divides order of G and gives the number of distinct right cosets, right? By our definition of divisor, something equals K times Q plus remainder of 0. K divides G, and that's by the factor of the index. However, this does not mean G has a subgroup of order K for each divisor K of order of G to the N, of order of G equals N. I've never really used that, but I think she could have like a true or false question on that. And finally, something good here is Lagrange shows us that there are a limited number of possibilities for the subgroups of a finite group. So that came up in the first question of the last homework, where we were told the index is 2. So then we know that there are only like a couple of possibilities for these subgroups. Corollary 8.6, let G be a finite group and let A belong to G. Then the order of A divides G for all A and G. So even if you don't even have to know what A is at the time. If you know what the order of G is, and you can find the factors that create that integer, then you can test just those cases for order of A, rather than going like all the way through like every possible number. So again, G is a finite group and let A belong to G. Order of A divides order of G. And if order of G equals K, then X to the K equals E for all X and G. So where E is the identity, not the constant, 2 point whatever. Proof how to do that, I kind of wrote down real quick for that first portion. The where are we? Here we go. Order of A divides order of G. If order of A equals n, then the cyclic group generated by A has order n by theorem 715. So n divides order of G by Lagrange. And that second one, if order of G equals K, then X to K equals the identity. You say let X be in G and let the order of X be n, then n divides order of G, which the order of G is K, so that order of G equals K equals NR for some R in integers. So then we can say, using that theorem 7.9 part 3, since we know from, what was it? Was it here? Yeah. Wait. Oh my gosh. But yeah, so order of G equals K, and we can say K is an R, since n divides K. So then, using theorem 7.9 part 3, since X to the K, what was I thinking? Yes, so we know that the order of, by part 1 of this, where, I know we just talked about it. Oh well. But I'm thinking of the where we just said that the order of G, that's the I'm thinking of the divisor stuff. Yeah, order of any element in G divides the order of G. Whatever theorem that was. So X to the K equals X to the NR, and then now we apply theorem 7.9. We say X to the N, the order of X to the N is R, or no, you just go ahead and use your it's not 7.9. I was mistaken. You just use your exponent thing rules. What was that? 7.4, I think. But X to the K, X to the NR, you can rewrite that using associativity as X to the N to the R. And we know that order of X is N, so now we have E to the R, which is just E. If A is congruent to B mod N and C is congruent to D mod N, then A plus C is congruent to B plus D mod N. So if K is a subgroup of G, then the translation of this is to congruence mod K, right? Instead of mod N, use mod big K. If A is congruent to B mod K and C is congruent to D mod K, then AC is congruent to BD mod K. This is false for some subgroups, but the special class of subgroups that this is always true is normal subgroups. So this card is leading us into 8.2 then. So we know what the right coset is. Left coset is basically the same thing, just flip the sides. So left coset is 8K, which is the set of all A K, little k, where little k is in K. And the right coset is this, just like flipped, Ka. Definition of normal groups: let G be a group and let N be a subgroup of G. N is said to be normal if the left coset equals the right coset for every element in G. So one of the shortcuts we know then using Lagrange and theorem 8.4, which was this, the union and the bijective mapping. If the index is 2, then, and 1/2 of the subgroups is normal, then the whole group is normal by theorem 8.4 with that union part, since they have to create G. And so if one of them's normal and those rest of the elements are left, then it's got to be normal as well. That was something covered in class thanks to Jonah. To show something is normal, the long way is find all of the left cosets and all of the right cosets and make sure that they're equal to one another. But kind of one of the faster things, if you know the group is abelian, then every subgroup of that is normal. So if N is a subgroup of an abelian group G and A is in G, then NA equals AN for all N in N, so that the right coset is the same as the left coset. And that works because the center of the group G star A is GA for all G and ZG. And that's the same the other way around. And this works because G is abelian. So since G is abelian, everything commutes, so everything's normal. Yay. Some more remarks. The condition of normality, the left coset equals the right coset, does not mean that each element in N commutes with every element in A. So an example that shows that we don't have little n A equals A little n for all N and N is let N be the rotations of D4, but rotation 3 star V doesn't equal V star or rotation 3 in D4. Also, another remark, right? We're still on the normal group remarks. If N is in N and A is in G, then for some N1, N2, and N, we have NA equals AN1, right? Since we just said that left coset equals right coset doesn't mean that they equal using the same elements N. So then for some N1, N2, and N, NA equals AN1 and AN equals N2A, because NA belongs to NA and AN belongs to AN, and the left coset equals the right coset. And that basically, to sum that up, we pick an element for the left or the right side and then see if they match. Theorem 8.7, every group G of order P is cyclic and G also is isomorphic to ZP. So this is really, even just in the review today with this professor, this was super important. So every group that has a prime order is cyclic. Every group that has a prime order is isomorphic to ZP. Theorem 8.8. If G is a group and the order of G is 4, then G is isomorphic to Z4, or G is isomorphic to Z2 cross Z2. A quick way to tell which one it is that if G has even just one element of order 4, it's isomorphic to Z4. If not, it's going to be isomorphic to Z2 cross C2. In theorem 8-9, if G is a group and order of G is 6, then G is isomorphic to Z6, or G is isomorphic to S3. The trick here for this one is if G is abelian, then G is isomorphic to Z6, right? The additive group of integers is abelian. But the snap groups are not abelian. Okay, so if we know G is not abelian, then G is isomorphic to S3, like automatically, if the order of G is 6. But if we're told G is abelian, and we find that the order of G is 6, automatically we know isomorphic to Z6. And the summary of those 3 shortcuts I just said, and all of the other ones that were in the notes from class. So if G is order as a prime order, then G is isomorphic to ZP. If G is order 2, G is isomorphic to Z2. If G is order 3, G is isomorphic to, pretty sure I meant to put Z3 there. Maybe I'll do that right now, because that's important. If G is order 4, then G is isomorphic to Z4 or Z2 cross Z2. And we know which it is because if G is just one element, order 4, then it's isomorphic to Z4. If it doesn't, it's Z2 cross Z2. Order 5, isomorphic to Z5, 6, iso to Z6 or S3, and we use the abelian to check that. And order 7, iso to Z7. So most of these are pretty intuitive. Oh, and order 8, that was left as an exercise, so I'm not too sure about that one. But they're all pretty intuitive. You just have to remember the Z4, the order 4, and the order 6. Theorem 8-10, let N be a normal group of G. If A is congruent to B and C is congruent to D mod N, then AC is congruent to BD mod N. And the proof of that, we say, suppose A is congruent to B mod N and C is congruent to D mod N. By definition of congruence from a couple sections ago, we have A B inverse is an N and CD inverse is an N. So you compute AC BD inverse and use Sachs-Hughes and associativity to show that it's in the cosets AN and NA, etc. If G was abelian, could move N around to get that pretty easily. If not, we have to use the full normality thing. Theorem 8-11, let N be a subgroup of G, then the following are equivalent. So if one of them is true, then all of them are true. So N is a normal subgroup of G, right? So that's, you're not gonna know that right off the bat unless they say N is a normal subgroup of G. Then you can use these other 4 things to help you in your proof to do something else. But otherwise, you have to use the other 4 things to prove number 1. 2 and 3 go together. You need to show, I think you need to show them both. You have to show closure. So A inverse NA is a subset of N for all A and G, N and N. And you have to show here that A inverse NA is in N. And then the conversely, you have to show to prove number 1, A inverse is a subset of N. That means we have to show A inverse NA is an N. I think I wrote that last part the wrong way around, but you know what I mean. 4 and 5, they go together. You show A inverse NA equals N, and you show A inverse equals N, then you show that N is a normal subgroup of G. Some remarks, note for 4 and 5, showing the equality. A inverse NA equals N doesn't mean, so like that before, like the normal subgroup doesn't mean all little a n equal a little n. So similarly here, it's the same deal. but that A inverse NA equals N means that A inverse NA equals N1 or some other element in N. And that could potentially be the same as N, but it's not necessarily. Some things that we know from exercises we did. If G is a billion and H is a subgroup of G and K is a subgroup of G, then HK is a subgroup of G. That was from the homework. Similar, and this next one was on the homework as well. If both H and K are normal subgroups of G, then HK is a normal subgroup of G. So some remarks with abelionism for normal subgroups. If G is a billion, then any subgroup H of G is normal. I think we've covered that before as well. Another remark with abelian stuff, the center of G is always a normal subgroup to an abelian group G. And we've covered that as well. So if G is abelian, then the center of G is always a normal subgroup, which kind of goes, that's kind of implied here, that if G is abelian, any subgroup of G is normal. And the center of G is a subgroup, so it's normal. Something important about theorem 811, this one. It's a big lifesaver because now instead of having to find every NA and AN, it's so much easier to check. For all G and G and for all N and N, if you check that G inverse NG is an N, which means that G inverse big N G is a subset of G, then N is a normal subgroup of G. And that's the exclamation point is me being excited. That's not factorial. I need to stop using that exclamation point. All right, and that's the end of this video.